Hey guys, in the previous video, I just introduced the simple concept behind proof composition, which is to implement a verifier into a circuit. Now I kind of want to generalize that to PCD and IVC, and I've kind of lied when I said that PCD is harder than IVC. Actually, IVC is the hardest one or the harder one to understand because you have to call yourself, and that's a bit trickier. But PCD is what I explain is PCD in general. So in your circuit, for example, you can have one verifier or several verifiers, and the VK they will use you can hard code different VKs there, and depending on your application logic, you might verify a proof using VKA or a proof using VKB or um, so that's sort of what PCD is all about. It's that you're you can choose dynamically what VK you want to use to verify the coming proof. Um, and so you can do different types of things. Um, do I have an example? Do I have an example? So, for example, in Mina, the cryptocurrency, Mina, there is a way to create a block in the cryptocurrency, which is to aggregate a bunch of transactions together. And basically, we have a circuit that's called a transaction snark or transaction circuit. And what it does is that it basically either verify um, a transaction circuits, either verifies a transaction, you know, verify VK transaction, or it verifies a VK merge, I guess, where a merge circuits is basically the verification of let's say two transactions to simplify things, but there's actually some recursion there, where you're actually merging two of your own instance. But I just wanted to point out that part where you're either verifying a transaction or merging two transactions that were verified. So that's sort of the dynamic part. In Mina again, also there's a user smart contracts, and this is called zkApps. And basically, people can deploy their own circuits, and we'll verify them, and the whole blockchain can run and verify a bunch of circuits. And so um, basically, there's a I guess or let me write it here in the transaction snark here. We actually or let's say the transaction here might verify um, any zkApps, any user zkApp, by finding in the state of all the accounts, which is a Merkle tree, if that makes sense. But you can imagine like a database of all the accounts. So you can imagine that as a database. For every address, there might be an actual VK of the circuits. And so when you verify a transaction that's executing a smart contract or a zkApp, you're actually finding in that database dynamically within the proof, you're actually finding the verification key that corresponds to that circuit, and then you verify a proof of that circuit, of that zkApp. Um, so that's how people can deploy their smart contracts, and everything gets verified dynamically. This is this notion of a PCD that I explained in the very first slide, um, proof carrying data. So now let me talk about IVC, incremental verifying computation. And the whole idea is that when you write circuits, you haven't compiled the circuit yet, right? Usually you take that circuit, you give it to a compiler, and it gives you the VK, the verifier key, and the proving key that you can use to prove or verify. But before you finish writing your circuit, you cannot compile it. And so if you cannot compile it, you cannot obtain that VK, If you cannot obtain that VK, you cannot hardcode that VK in your circuit. So the way IVC work is that you get around that by, oh, that's not very clean. You get around that by obtaining your VK dynamically by passing it as public input. And that's basically the trick behind IVC. That's how you can recursively call yourself. You just pass the verifier key dynamically via public input. That's all there is. So I'm gonna stop the video now. I think, well, actually, let me give you an example of IVC, which I think adds more color to this whole thing. But again, in Mina, if you know blockchains, you have a Genesis block, and then you just add blocks on top of it, and every block is just a list of transactions. Block. And if you want to synchronize to the blockchain as a client, you start here and you go through every block, and for every block you look at their transaction, you re-execute them, and then you go to the next block and you have to verify all of that. In Mina, for every time we create a block, we basically create a proof, and that proof verifies in a circuit all the transactions, verify the signatures of the transaction, that they're valid and everything, and then creates a new state, and also verifies the previous proof. And so by verifying a proof in Mina, the latest proof in Mina, you get a verification of the whole chain since the beginning of time. And so you can sort of, it's kind of this idea of compressing the whole history and just having a single proof on the latest state of the world, the database of all accounts. It's a few kilobytes, and that's the idea of using IVC to compress some sort of computation that never ends. So yeah, hopefully that makes sense. IVC is really cool because you can compress data, and PCD is really cool also because you can create these trees. Here I give the example of a tree of transaction. You can sort of split your computation, or you can have functions calling other functions. That's an example I gave here in the beginning. Or you can have smart contracts on blockchain as well by dynamically allowing people to create new circuit and load them in the system. So now you should know how this thing works at a high level. IVC, PCD, they're all like building on top of this very simple idea that you can just implement a verifier inside a circuit. I'm gonna stop now for this video, and in the next video I'm going to start talking about implementation details, which might be of interest for some people. If you don't want to know more about the technicalities, you might stop here. I think this is a good point to stop. Otherwise, I'll see you in the next video.